In a controlled laboratory setting, a cement-stabilized earth block perfectly matches the compressive strength of standard industrial concrete. Yet when these exact structural parameters are entered into modern building performance software, the systems return undefined parameters and sequences of error codes. Earthen architecture is excluded from the institutional frameworks that govern modern construction. Insurers, lenders, and building codes lack the necessary categories to process it. Confronted with these software failures and regulatory rejections, structural engineers often conclude that the material itself is structurally unreliable. The core challenge is institutional legibility. Earthen material is currently being forced through a rigid regulatory framework that was never designed to account for its specific properties. A 2026 literature review by Afaha, Oguke, and Aka surveyed the global landscape of earthen building standards to quantify this disconnect. 74% of existing global codes address only a single isolated earthen technique, such as adobe or rammed earth. Only 27% of these codes cover stabilized systems, the very methods most applicable to modern engineering. Despite these regulatory divisions, the underlying soil mechanics and physical behaviors remain consistent across all methods. By fragmenting these techniques into separate silos, the regulatory infrastructure creates a system that ignores the shared science of the material. This fragmentation dictates how a project is engineered as soon as a practitioner crosses a jurisdictional border. The American standard, ASTM E2392, relies on laboratory-engineered design and sterile structural calculations. Its engineering logic is derived from the behavior of conventional, hollow-core concrete masonry. The SADC standard in Southern Africa operates from an entirely different paradigm. It utilizes field practical assessments, such as rolling soil samples between the palms to judge moisture and clay behavior. Standards in Germany and New Zealand introduce further friction, using different metrics for soil classification and seismic stress values. While neither the laboratory nor the field approach is incorrect, their incompatibility leaves the engineering community without a cohesive structural language. Even progressive earthen codes often remain siloed, creating failures when they encounter modern building techniques. The New Mexico Building Code mandates a minimum compressive strength of 300 psi for compressed earth blocks, roughly the pressure of a loaded pickup truck distributed across a single block. To maintain this certification, builders must conduct structural testing every 5,000 blocks. But the code contains a specific structural blind spot. Its provisions apply exclusively to compressed blocks. Modern earthen plotex frequently use composite systems, such as rammed earth walls with compressed block infill. In these hybrid scenarios, engineers must stitch together contradictory codes, leading to regulatory dead ends that halt project approvals. Mismatched codes lead to inconsistent test data, which practitioners often misinterpret as material failure. A 2014 study by McGregor and colleagues examined whether this variance was caused by the material or the testing process. Researchers extracted 48 identical rammed and compressed earth specimens from a single batch. These blocks were sent to different laboratories for standard durability tests, including simulated rain and soaking. The results varied by more than 40% across labs, despite the material being identical. This 40% variance proves that the testing apparatus itself is unreliable, not the earth. Architects and engineers cannot specify a material they cannot reliably measure, which prevents the material from being codified. This problem of measurement also compromises the digital models used to predict building performance. Practitioners rely on hygrothermal simulation software to secure energy ratings and building approvals. This software produces clean, predictable moisture absorption curves over a 12-month simulation. But when compared against sensor data from actual rammed earth walls, the curves failed to match. The software underestimated the wall's ability to absorb and release moisture by 18 percentage points. These models are calibrated for manufactured materials, like concrete and insulation, that operate within narrow industrial parameters. Earthen materials behave with perfect predictability, but because their logic is not codified into these tools, engineers are left with false negative data. This institutional blind spot creates a global macroeconomic bottleneck. Roughly 1/3 of the world's population lives in earthen structures. Multi-story Tulu structures provide permanent, high-density habitation, demonstrating the viability of earth on an urban scale. The Great Mosque of Janeh further illustrates the capacity for complex, vertical earthen engineering. In regions across sub-Saharan Africa, South Asia, and Latin America, governments lack nationally recognized codes, leaving them unable to regulate or improve existing infrastructure. Codifying earth is a developmental necessity to make centuries of existing built environment visible to governing institutions. Today, practitioners must navigate this broken regulatory system through defensive practice. Professionals must aggressively document their own testing to offset the deficits in standard codes. This requires a clear understanding of the limits of borrowed standards, such as the laboratory focus of ASTM versus the field focus of SADC. Builders must be prepared to educate regulatory officials and inspectors throughout the approval process. The long-term solution is a harmonized international framework that covers all earthen systems under a single coherent structure. This effort starts with the empirical baseline. Cement-stabilized earth can match the compressive strength of concrete. The data proves the material is adequate. It is now the responsibility of engineering institutions to widen their perspective and learn how to read it.